Every major AI vendor today implements isolated proprietary execution loops. There is no standardization in tool calls, sandbox boundaries, or event streaming. Engineering teams relying on disparate SDKs like Claude Code, Codex, or Goose are forced to maintain multiple bespoke architectures just to keep their AI pipelines running. Omnigent addresses this engineering bottleneck directly. It operates as a universal multi-harness agent gateway, designed to unify these disparate vendor ecosystems into a single, cohesive control plane. The core architectural thesis is simple. True orchestration requires entirely separating the model's intelligence from the execution environment. This diagram visualizes Omnigent's solution. The control plane is split into two distinct layers, a multi-harness adapter layer that normalizes the inbound chaos, feeding directly into a highly structured native gateway runtime. To prove the efficiency of this architecture, we will deconstruct the precise six-stage data pipeline of a single AI request passing through the Omnigent runtime. By centralizing the gateway, engineers immediately reclaim strict control over security, state management, and command execution, regardless of which large language model is running under the hood. The six-stage pipeline begins with intake and routing. A user prompt enters the system through either the CLI console or the native gateway server. The routing engine inspects the incoming arguments and decides whether to hand execution off to an external adapter shim or to route it through Omnigent's native React workflow engine. This schematic illustrates the immediate next step. Before invoking any LLM, the system performs context resolution by querying the Alchemy Lab and Postgres database layer. The database search actively locates the latest compaction checkpoint. This allows the system to efficiently assemble the LLM message array with precise historical context without instantly overloading the token window. Retrieving state from a durable SQL backend ensures deterministic session recovery. It completely eliminates the risk of relying on a fragile, in-memory script loop that dies the second a server restarts. Once the message array is successfully assembled, Stage 2 sends the payload to the configured LLM client for inference. This animation shows the multi-harness adapter intercepting raw, proprietary data streams returning from the LLM. It normalizes these formats into a strictly typed ExecutorEvent protocol, categorizing them into uniform structures like TextChunk or ToolCallRequest. These events are instantly broadcast outward to connected clients. To maintain stability during heavy inference, the SSE broadcaster automatically caps subscriber queues at an absolute limit of 1,024 events. This strict cap is a queue overflow defense. It prevents unbounded memory growth and system crashes if the UI consumers lag behind the sheer speed of the LLM's output. By strictly normalizing event streams and defending the broadcast queue, Omnigent isolates the front-end application from back-end vendor chaos and silent memory leaks. Stage 3 introduces a critical boundary. When the LLM emits a tool call request, like asking to execute a terminal command, the execution loop must immediately halt. Relying on natural language system prompts to prevent an AI from executing malicious commands is an insecure practice. Models can be easily tricked into bypassing text-based instructions. This diagram outlines Omnigent's alternative. The tool request is routed through declarative Python policy evaluators instead of trusting the LLM's behavioral adherence. These native pre-tool hooks process the request and return explicit programmatic decisions, allow, block, or ask, before any execution can proceed. Shifting authorization from easily manipulated prompt instructions to explicit Python code policies guarantees a level of deterministic security that the LLM simply cannot bypass. Once a tool is explicitly approved by the policy engine, we move to Stage 4, sandboxed command execution. Approved commands do not run directly on the host operating system. This cross-section visualizes Omnigent's use of Linux Bubblewrap. Approved commands spawn exclusively inside isolated mount, PID, and UTS namespaces. The first OS defense layer locks down the file system, mounting system libraries strictly as read-only and masking sensitive workspace.files completely. The second layer of defense relies on a hardened Seccomp BPF syscall filter. Applied over the PR set no new privileges flag, this filter operates as a restrictive syscall barrier between the isolated process and the Linux kernel. It explicitly blocks the process from creating unauthorized raw network sockets, loading kernel modules, or executing any form of privilege escalation. Because the security is enforced at the kernel level, Even a compromised model or a malicious script is physically incapable of damaging the host infrastructure. After the sandbox tool finishes execution, the pipeline enters stage 5. The output is wrapped into a ToolCallComplete event and immediately persisted to the SQL database. This leads to the fundamental problem of long-running AI sessions. Verbose build logs and massive test outputs will rapidly exhaust the LLM's maximum token context limit. This ladder diagram tracks stage 6. Omnigent runs the session history through a progressive 3-layer compaction pipeline. In layer 1, surgical clearing wipes massive, stale tool payloads while preserving metadata. In layer 2, older conversational turns are condensed into a structured LLM summary checkpoint. Layer 3 is passive truncation. This is a final, hard tail cutoff, used exclusively as a last resort if context limits are still breached after clearing and summarization. Structuring memory through 3-layer compaction stops context deterioration. It ensures an AI agent can iterate indefinitely on a complex software project without suffering arbitrary memory loss or system failure. This final architecture map displays the completed 6-stage data pipeline. By isolating the model from the execution, Omnigent achieves a stateless boundary between intelligent reasoning and system operation. To protect the development lifecycle itself, the entire framework is encased in explicit testing guardrails. If Omnigent detects a PyTest execution, it instantly forces the runtime to use ephemeral in-memory databases, completely blocking any attempts by the test suite to bind to active development or production ports. This deconstruction leaves systems architects with 3 fundamental principles for building production-grade AI infrastructure. First, universal adapter normalization solves vendor lock-in. Enforcing a strictly typed event stream ensures your interface code remains stable no matter which backend model you deploy. Second, true execution security requires kernel-level OS sandboxing and declarative code policies. Relying on prompt-based guardrails to protect system infrastructure is a critical engineering failure. Third, sustainable context management requires structured, multi-layer compaction paired with durable SQL persistence to prevent token exhaustion and data loss. Omnigent demonstrates that a deterministic execution harness allows for secure, multi-vendor agent deployment using the frontier models available today.